Hi, James. How you doing? No signal. No, no, I don't think I need them on. I mean, it's up to you if you find it works better for your audience, but triplicate? Okay. That's interesting, the aspect ratio. You get the 16:9. Yeah, that's fine. My other talk is 16:9 format because it was done for SIGGRAPH, so we'll see what happens.
Oh, are they setting up their format?
Yeah, they are now. So, okay, that's the other talk, which I'll do at the end. So I'll just go back to. Okay. Sure.
Try to go from 4 to 5. Try to round it up.
Oh, sure. Yeah.
No, I didn't. Here? It's only because it's so close. Yeah, you're out Okay. Thank you all for coming. I'm very happy to introduce Rick Szeliski. Rick is a distinguished scientist at Microsoft Research in Redmond, where he directs the Interactive Visual Media Group.
That's right.
Have that right?
Yep.
And they do all sorts of exciting work at the intersection of computer graphics and computational vision and learning statistical modeling, bringing data into these problems. Rick has done a really great job over the years of not only doing great work, but explaining that work to others. One of my favorite papers of his came out of his PhD thesis at CMU. It was called Bayesian Modeling of Uncertainty in Low-Level Vision. I think it was really ahead of his time. And sort of, our models have gotten fancier, but often I think we're a little less thoughtful these days than he was there in terms of thinking about how you express what the models do and don't know. And more recently, a couple of years ago, he published a very nice computer vision textbook that brings together conceptual ideas with really linking them to state-of-the-art applications. And you're going to hear a bit, I think, a lot more about those links today in the world of image-based modeling. So, great.
Thank you very much, Eric. So thank you. I'm honored by the invitation to come here and give you guys a talk. This talk is kind of a retrospective on the last 15 or 17 years or so of the field of image-based rendering, which is a subfield of computer graphics, and the parallel field of image-based modeling, which is what we do in computer vision. So let me just start sort of with a very quick retrospective on how far have we come in these last 15 or so years. So this isn't the first piece of work in image-based rendering, but it's one of the most foundational. So there was a paper at SIGGRAPH in 1996 called Light Field Rendering by Pat Hanrahan and Mark Lavoie at Stanford. And then Michael Cohen, Steve Gortler, myself were authors on a parallel paper called the Lumigraph. And the idea here was that if you take enough images of a 3D scene, then by basically stealing pixels from different images, you can actually create new views. And I'll go into the math of this a little bit later. But this was one of the early pieces of work that proposed that this is an interesting alternative to traditional computer graphics, which says something like you build a 3D model, you put lights on it, and that's how you render. Something like 5 years later, we were looking at problems like environment matting, where here the question is, we know that things like glass refracts light. But if we don't have a synthetic model of a glass and we have a real world model, how can we capture that information? Can we do it for something like a glass where you're pouring in water? Can we create a video that essentially captures the refractive properties of flowing water? And we did this by having different backgrounds, like the checkerboard there. And we would capture enough information so that when you lit the scene with a synthetic background, it would create a very plausible image. So this is another kind of image-based rendering, where we basically capture now an object instead of a scene, and then we change the lighting. A very different example is 5 years later, a project at University of Washington we called phototourism. And in this project, what we did was we took a large collection of images. This is from the Central Square in Prague. And we arranged them in 3D. We basically built a 3D model. And now you can go into the upper right corner and navigate the map to say, I want to move here. Or you can select a particular building and say, I want to have a closer view. So as you navigate the scene, you're basically moving around and you're seeing a sequence of photographs. But the way the system is moving the camera makes you feel like you're moving in 3 dimensions. When you go to a website and you see just a big stack of photographs, it's hard to navigate or figure out what you're looking at. Here we sort of embed the photographs into a 3D world. So again, an example of taking images and rendering a virtual experience from those images. And a lot of this work is based on 3D computer vision. And computer vision doesn't always work that well, which is why in that example, our proxies for images were these flat planes. In this example, we're building a more detailed model of the actual sculpture. But even there, outside of the sculpture, the computer vision system isn't doing a very good job. So what we do is we render the rest of the world in this kind of pointillist thing. And so here we're playing with the idea that not all rendering has to be super realistic. It can be a little bit non-realistic. And so this is yet another way. You can use images, but then combine it with this sort of what some people in graphics call NPR, non-photorealistic rendering. And this is the last example. This is a paper that was just published in October by a student at the University of Washington and Steve Seitz and his team at Google. They call this photo tours. And if you go onto the Google Maps website and look for photo tours, there will be tourist destinations. This is basically an outgrowth of our photo tourism paper. They create these very nice 3D models, and then you can sort of navigate from viewpoint to viewpoint. So that sort of gives you a very quick overview. And in this talk, what I want to do is kind of go through the history in a little bit more detail, landing in a couple of spots to show you some of the basic optics and mathematics and other representations that are used. And I'm going to go through a series of more and more sophisticated papers. The last slide here, I'll talk about what I think is one of the big outstanding open problems, which is how to deal with reflections in the world. So if you look at the whiteboard there, you can see the sort of glossy reflection of the ceiling lights. Even the armrest that you're putting your arm on, there's definitely a glossy reflection of something else in there. And most of these systems don't deal with that very well. So the last thing, I'm going to actually switch slide decks and show you a little shorter version of what we presented at SIGGRAPH last summer. So that's kind of the new work. Everything else is retrospective and historical. And if you have questions as we go along, please feel free to stop me. I have a fair amount of work to review, but I'm also happy to sort of lead this in any direction you find interesting. And I do plan to wrap up early so we can have a more interesting question and answer session. So let me start with a little bit of prehistory. Those of us who are doing computer vision, I was still at Carnegie Mellon working on my PhD, and we were already taking sequences of images in the mid-'80s and reconstructing 3D models and sort of pasting the original image back onto the 3D model and then moving the camera around synthetically to see what it would look like from different points of view. So in computer vision, this idea of sort of taking the world and building a 3D model and then rendering was already there. In computer graphics, there was work being done around the same time on what people called view interpolation. So the biennially is actually a reference to the sort of the significant paper on image morphing. So you're all familiar with image morphing examples, like in certain fantasy movies where a character's face turns from human into a tiger or something like that. So that was sort of an early example of, again, a kind of image or video-based rendering where you took some original content and then by digital manipulation made it look like something else. Chen and Williams actually took this into the realm of 3D. They were the first ones to propose that you could build a computer graphics system where rather than always rendering everything from polygons and lights, you could pre-render the scene. And on low-end hardware, which was the max of that time, they were working at Apple, you could sort of pre-render a complex scene and then do very small shifts of viewpoint by just basically moving those rendered pixels around. So that was kind of the beginnings of image-based rendering. Around this time, when I arrived at Microsoft in 1995, we started looking at the problem of panoramic image stitching. So Apple had just come out with a system called QuickTime VR, where you could put a camera on a tripod and rotate it by precise 30-degree increments, and there was software that would stitch it all together. We asked the question, can you do this with handheld photography? And we came up with one of the earliest systems. Now, I'm sure, as most of you are aware, either your camera or your cell phone has this kind of thing built in. So how many people have played with some kind of stitching application on their phone, right? How many people have tried Photosynth? Okay, about half of those, right? Photosynth is the system we developed at Microsoft based on this long line of research. And it's the kind of software that you find in your phone, but also a lot of point-and-shoot cameras. And it's a simple example of image-based rendering. You take a bunch of images, and then from that, you render an interactive scene, right? You can pan around and see the scene from different things. And the technology here relied on a couple of key technical breakthroughs. So there were things like the ability to interactively view, that was computer graphics. Then dealing with general camera motion, that was some of the research we did at Microsoft. Compensating for parallax, what happens, those of you who've tried doing stitching, if you go and swing your camera like this, it doesn't always work very well because what you're actually doing is capturing a three-dimensional scene that can't be quite rendered flat onto a single thing. So the best way to do it, if you really want a high-quality one, is to just rotate around the camera itself. But we have ways of dealing with parallax. And really some of the breakthroughs were work by Brown and Lowe at UBC, who showed that using these kinds of feature matching techniques that David Lowe had developed, SIFT and so on, you could build fully automated systems to do this. So a whole series of technical things. And I won't go into detail, but just to sort of indicate that even something that seems as pedantic as or pedestrian as your image stitching has tons of very interesting mathematics and computer vision research. So image stitching is actually one of the examples, the first sort of programming assignment we use in our computer vision class at the University of Washington, because it has all of the interesting components. There's feature detection, feature matching, image warping, image blending, and these are all the parts you need to put together to create one of these systems. So today we see that there are websites where people share huge panoramas. So Gigapan, for example, took this, I don't remember what it was, 20 or 200 megapixel panorama of the inauguration. There are websites like VR 360 Cities, where photographers take these beautiful panoramas and share them with others. And of course, there's the Photosynth website, which started off initially as a version of phototourism, but is now also a place where people can upload and host and share their panoramas. So you can think of panoramas as a very simple kind of image-based rendering system. The input is an image. The output is a larger image, potentially rendered on a cylinder or a sphere that you can navigate interactively. But if you're sort of a mathematician, you say, well, we're really just moving from a series of 2D manifolds to one larger stitched 2D manifold. So how can you sort of go from 2D to something bigger and more interesting? So one thing we did was we said, well, a panorama is interesting, but what's even better is a panoramic tour. So what about if we could take a 360 camera and walk around inside a home and then be able to see the home from a continuous set of viewpoints? So if you go to websites where they're selling high-end houses today, you will probably find a couple of panoramas, and you can sort of jump from one room to the other. How could you make that experience a lot more seamless, to just basically go and be able to continuously move from room to room? So at the time, there was no reasonably priced 360 video camera available. So we had Point Grey Research in Vancouver build us one. They've since been selling this thing under the name of a Ladybug. And this is actually one of the cameras that was used for some of the early street scanning. We put the camera on a little tripod, hooked it up to a disk drive and a laptop, and then we pushed this thing around in the house. But it got very tiresome quickly to sort of crouch down so you were below the camera as you were pushing it around. So we developed 2 series of automated systems for moving the camera around. One was a robotic cart, and the other one was a researcher. This is Sing Bing Kang. And you know, this picture always gets a big laugh, you know, because how geeky can you be? You know, who would ever walk around in public with a bulky helmet and a camera stuck to the top of their head, right? Well, my son does, right? This is ultra cool, right? GoPro camera. If you are a mountain biker or you are a downhill skier, you own one of these, and you are filming the world for your best tricks, and you're filming your friends, and you know, this is all first-person video for adrenaline athletes, right? So you can laugh. This is just that young generation of athletes, right? We're all computer people. We don't get outdoors. We don't do this kind of thing. Unless, of course, Google is right, and you'll all be wearing these things a year from now, right? So this is Google Glass. They haven't yet started selling these things commercially, but their vision, if this becomes a success, is that we will all walk around with cameras and displays. And so this idea of capturing the world and sharing it with others is just, it's coming, right? It's coming in many forms. It's coming for sports videos. And of course, it's coming for commercial scanning, which is what we at Microsoft and Google are doing when we drive our vans around in cities and capture these panoramic photographs, right? So this kind of idea that you take panoramas and now you turn them into movies basically is here, right? It's not everything. You don't go to a cinema to see a 360 wraparound movie. I mean, you can see them at Disneyland and places like that. But most of us have at least looked at Street View once or twice when we wanted to see where that store was, or you know, the apartment I'm going to rent in Paris. What does the street look like? That kind of thing. So this is, I would claim, a sort of very commercially important example of image-based rendering, something that we in the graphics and vision communities invented and commercialized. So let me now go from this, which in some ways is fairly easy to describe because it's just images and stitching them together, to the fundamental mathematics behind light fields and lumigraphs. So there aren't actually, I don't think I have any equations in this talk, but I will talk a little bit about geometry. So this will be sort of a throwback to your introductory computer graphics class, right? So the question is, if we have a scene, and what's happening in this room is, you know, a lot of photons are bouncing around, can we somehow capture this so that later you could recreate the essence of being there, move around and see what the scene looked like, right? So the classic answer to this question is you use 3D vision and you use graphics, right? You basically take a lot of pictures and you recover the camera pose, you build 3D models, you extract texture maps to put on the 3D models, and then you synthesize new views, right? So basically, you start with computer vision, and from some images, it builds you a 3D model, and then computer graphics renders that model, and this is what happens when you put it together, right? But this is an idealized picture of what really goes on. When you really try it today, computer vision gives you this rough, blobby model that has holes wherever there's a reflection or there's a lack of texture or something. So it's a very imperfect model. And even if you give the computer graphics a perfect model, it won't necessarily render a completely realistic scene because it can't capture everything. So the answer, and this was sort of the basic insight with image-based rendering, is that if we combine a crude 3D model with a large number of images, then you can create in-between views that are very realistic. And the mathematics behind it goes something like this. So let's assume we're trying to capture something. So here I'm going to be outside a scene looking from the outside in, right? You can also do this if you're inside looking out. But let's say there's a scene, so it's a table and it has, you know, a shiny bottle on it and a laptop. And I want to say, what does it look like from all the viewpoints around, right? So you might have to say, well, how many images do I need? Do I need a photo from here? Do I need a photo from back here? So a photo is like a two-dimensional manifold. It's a, you know, if you had continuous pixels, it'd be a piece of a two-dimensional function, right? And the number of locations I could grab it from is, well, there's 3 locations, 3D. And of course, at each location, I have a certain angle of view. So ignoring zoom, there's 3 dimensionals encoding the thing. So I have to take a picture from all 6 degrees of freedom. And it sort of feels like there's some 8-dimensional space that you have to capture, right? But in reality, it's not. It's relatively easy to argue, to show that it's only a 4-dimensional space. So any light ray leaving this laptop heading in a particular direction can be parametrized by just 4 degrees of freedom, right? Because there's sort of the direction, which is 2 degrees of freedom, and if you make it intersect some plane, there's where it intersects that plane. So it's a 4-dimensional, the light field is a 4-dimensional complex. This is just a 2-dimensional cross-section. And one of the easiest way to see that is to invoke what's called a 2-plane parametrization. So you sort of imagine if I had a camera moving around in a 2D plane, and I took a whole bunch of pictures, even though you might say, well, I don't know how to project a view from back here, the fact is you can, because what you can do is once you've organized this and you want a new view, you can basically take, this is just sort of showing that there are all the rays. If I want a new view, for every ray I want for my new virtual camera, I can go and look it up in the original thing, right? I just have to say, where did it hit the first plane? Where did it hit the second plane? And I look up that color value, and I'm done, right? So it's kind of good news that this light field isn't this amazingly huge, complex thing. It's only 4-dimensional. We're used to dealing with 3D volumes when we have medical data. So this isn't that bad. And some of the early experiments involved waving a camera around an object on sort of a hemisphere. And if you paper it with a dense enough set of images, you can actually go and look, you know, see what it looks like from further away or closer in. So for the rendering time, we basically just for each ray, we go and we look up the ray. But it turns out that this is a unnecessarily simplistic view of the world, which requires you to have very dense sampling. If you sort of want to be able to move the camera everywhere, the number of samples, in other words, the number of photographs you need, ends up being very dense. Essentially, you have to move the camera no more than the amount which would have 1 pixel move, any point in the image move by more than 1 pixel, which can be a very small amount. But if you actually put in a 3D model, then you can get by with many fewer samples. Because what happens now is if I want to know what color should this ray here be, so I've got, just get my mouse over there, there. So if I'm sort of asking the question, what color should this ray be, what I can do is I can intersect the ray with the 3D surface, and then I can say from each of the nearby cameras, where did it see it? And this makes a huge difference in the quality of the interpolation. So I think in computer graphics, there's this slight tendency, you found a magic bullet, it's called the light field, we're going to do this. And we're seeing the same thing being played out today with things like light field cameras. When you look at the mathematics and the descriptions, they say, we don't need to do computer vision, all we have to do is take this pixel from here and this pixel from there and put them all together in an image and we're done. Whereas in reality, for any given number of images, if you have a 3D model, the better the 3D model, the fewer images you need, or conversely, the higher the quality. And we'll get back to this, you know, near the end of my talk when I talk about modeling reflections, where I will claim that if you can come up with a better model for how the light is moving, namely 2 proxies, which is even better than 1, you get better results. So it's sort of, this is one of the sort of insights I would claim that is important to understand, and it's sort of, it's accepted by most computer vision people because we're comfortable with the idea of making 3D models. But in some parts of computer graphics, they still say, no, we can do this without 3D modeling. So I'll show one more slide on the light field here. What you're looking at is basically the volume of images that would happen if a camera moved to the right. And if you stacked all of these images, as you basically, you can just do this experiment right now. You can move your head back and, you know, sideways, and you'll notice the person in front of you and the person 2 rows in front of you are moving and occluding each other at different speeds. That's what we see here in these horizontal stripes. This is a horizontal cross-section through this 3-dimensional volume. In computer vision, it's called the epipolar plane image, EPI. And it's well understood in computer vision that if the camera moves sideways, rigid objects in the scene trace out linear paths. But what's less well sort of acknowledged is that in some areas, like in here, what happens is you get a kind of additive mixing because we're looking through part of a glass bowl and there's a wood texture underneath it. And what's happening is both of these things are superimposing on top of each other. So this is an example of transparency. So, you know, the obvious effects are parallax, which is that things move at different speed. There's occlusion. You know, when one thing hides another, it disappears. But then you have things like the transparency effect. So I'll come back to that near the end. OK, so I'll mention a few other interesting variants on the basic lumigraph. So the basic lumigraph said one of the simplest ways to organize our pixels are to put them on two planes. The unstructured lumigraph, which was follow-on work by Chris Buehler and collaborators at SIGGRAPH, said we can just start with the original images. We don't have to resample them onto this two-dimensional parametrization. But from the original images, we can pick out the right rays and, again, using a crude 3D model, re-render it. So this is, I think, an important advancement over the initial work. And then another piece of work I really like is called surface light fields. This is basically underappreciated because there haven't really been any follow-on papers. But here the idea is, again, if we have a four-dimensional function, we can choose where to put our samples. It turns out that a very intelligent place to put your samples are on the surface, because if you look at all the light coming out of a surface, it will more or less have the same color. If I'm looking at something like this fish here, you know, regardless of where I look from, this yellow fin will be yellow. Now, it might have a little bit of white contamination from the gloss, so it'll be some mixture of white and yellow, but it certainly won't be red, right? So the color is the same. And in fact, if you look at how does the appearance vary as an angle, it varies very slowly when you're in the Lambertian region, and then it'll have sort of a quick blip when you reach past the specular highlight, which will depend on where the lights are in the room and other things like that, right? But you can really compress the whole thing, and it already encodes the 3D. Now, of course, for this to work, you have to know what the 3D geometry is, so that might be one of the reasons it's not used. But I think this, you know, if students are looking for interesting research in this area of light field rendering, I think this is still something worth picking up. Okay. So what have we sort of looked at so far? We've looked at the light field, which is a four-dimensional thing. We've looked at panoramic videos, which are 3D. And there are these, what people call 2.5D representations, which are basically sort of, if you take an image and you add a little bit of extra depth to it, then you can think of it as a two-dimensional beast, but it has depth information. So what comes out of a Kinect scanner or range scanner these days is color, RGB, and depth. And so you can think of it, again, as a 2.5-dimensional thing. The Kinect scanner does not give you a 3D volume, right? It gives you an image, but the image has depth. And so what you can do with that depth is you can render from it. So one way of doing this is just have a regular array of pixels and allow sort of for 2 or 3 different color and depth values at each pixel. And then from that kind of a representation, which is called a layered depth image, you can render new views. You can basically move your camera like down here and then look at all the other pixels and render them. And there's an easy way to do the rendering without triangle rendering, just using something called splatting. Another approach, which is closer to this idea of layered representations, I know Eric is still doing a lot of work on layered representations, is you sort of break up the world into little local pieces. They're not full 3D models, because from a small number of images you won't have seen around the backside of the object. But each little model can be either flat or it can have its own little shape. And then from that we can render it. And sort of a variant of this was the basis of what we called virtual viewpoint video. So virtual viewpoint video was a paper we presented in 2004. And one of the scenarios we wanted to answer was, well, can you, and actually the vision, the sort of application vision had for many years before this been proposed by Takeo Kanade at Carnegie Mellon. He called it virtualized reality. Can we film a sporting event so that you can be right with the basketball player in the NBA? They did a little pilot at one of the Super Bowls where they put a bunch of cameras around the stadium. And then when they want to do a replay, they could basically jump between the various cameras while fixating on the player of interest and sort of show you a replay. And they could say, was the player out of bounds at the time they caught the football or something like that. But you know, other applications, you know, we haven't really seen a lot of commercial systems, but it wouldn't surprise me if we do start seeing things like this, for example, for instructional video. So we sort of wanted to play in the space to capture something. So we built a system that recorded multiple video streams that were synchronized, and then we wanted to see how far we could push the photorealism. Because if you look at some of these renderings where you change your viewpoints, sometimes they look like the models are a little bit lumpy and you can see artifacts. We wanted to see whether we could really drive photorealism and have reasonable compression and maybe sort of start prototyping what could become the basis of 3D TV in the future, sort of interactive, variable viewpoint TV. So the system we built, again, working with Point Grey, we bought a number of cameras that went through synchronizers to a bank of hard drives. And then we did stereo matching between all of these cameras. And for those of you who've looked at stereo matching, sometimes it's easy because if you have something like, a nose on a person's face, it's pretty easy to find it in the other image. Even though the head is tilted a little differently, you can do that. Sometimes it's harder, like when you have an untextured pixel, where does that go to? That's a lot harder. Or it can be really hard because you have like a face in this image, in the other image the face isn't even there, it's occluded, right? So Larry Zitnik built a stereo algorithm based on segmenting the image into different colored pieces and then matching them up. But what we found in our initial renderings was that if you just built a 3D model for an image and then tried to generate a new view, you would see artifacts. And maybe I'll just jump ahead to sort of show you. This is what the artifacts look like. If you basically take one image and sort of move it synthetically to an in-between view, the image on your left shows these sorts of boundary artifacts that are there because each pixel is either at the front depth or the back depth. And you're not modeling correctly the pixels that happen to be half of the color of the front and the back. So the way we did this was we went back to a topic that had recently been studied in the early 2000s called image matting, where you basically say, let's represent, instead of a foreground surface and a background surface, where some of the pixels are mixed, let's represent it as a foreground and a background. And then we're going to extend the background to be a little bit fatter, which when you have multiple cameras you can do, because you can see around the back of the object from the side view. And then let's solve for the front in such a way that some pixels that have partial transparency get that partial value stepped in. So in computer graphics, this is very typical, right? Everyone does anti-aliased rendering. If you're going to sort of render a sprite and then move it around in a scene, it always has a soft alpha matte. So it's very well understood. But in sort of three-dimensional image-based rendering, this was the first system that did it. And the end results were very good. So with the matting, the image on the right there, you couldn't really see the artifact. So we were able to produce a representation that basically was the original color video with a depth map that could compress quite well because there just isn't nearly as much complexity in depth as there is in color. And these very thin boundary layers that would encode where there's extra color and extra opacity along the boundaries. And then we produced a video. So in this video, you're going to see, you saw the setup, which has 8 cameras. So if we produced a video that just sort of jumped from camera to camera, you would see an interesting video where you could see some dancers and you could jump your point of view. You're going to see something that looks much smoother because we're doing the kind of smooth view interpolation. And the trick is, can you see any artifact that would cause you to believe that this wasn't taken from a moving camera, that this wasn't a studio with some sort of computer-controlled camera that, well, for one thing, a computer-controlled camera probably couldn't do that, right? Because how would it freeze the time and keep changing the viewpoint, right? So we can freeze the time because we basically take a frame and we're just smoothly interpolating the viewpoint. Or we can synthetically do crossfades of different people, and we can do things like z-buffering, right? So this guy's going to do a spin of some sort, and we're going to like take his spin and like do some kind of a weird, oops, anyway, I wanted to freeze it there, but just a weird z-buffer composite, right? So we're basically showing that if you want to, with enough computation, you can take a series of videos and turn them into three-dimensional video, where each frame has depth and actually better than depth. It has enough information to resynthesize nearby viewpoints and interpolate between them. So I think it's an exciting line of work. I think it's a matter of time before it gets picked up commercially because we're starting to see more 3D TV sets in the home. Eventually I expect there will be some applications where people in studios will say, yes, let's do this. Maybe initially for instructional video or something like that. But it's another, I think, very promising aspect of image-based rendering. Yes?
How are you computing the boundary layers then?
So the boundary layer was computed by basically solving a matting problem. So what we have here is, let's say that I know there's a depth discontinuity, right? What I can do is I can reconstruct the background for a couple of pixels behind the discontinuity, because I have enough views from the side, so I can reconstruct the background. If I know what the background color, and I know what the foreground color is, so whoops, I wanted to go backwards here. So let me just show you this image here, right, which in this light is very hard to see, but this is part of a person's arm against a dark blue background, right? So if I tell you the dark blue background is here, all the way behind, and I tell you the foreground looks like this, right, then you can basically say how much blue and how much beige do I have, and that gives you the soft alpha. So it's natural image matting, essentially, right? But before you can do the natural image matting, you have to get the depth out. And you do the depth using traditional stereo, and it kind of will still get the right depth here because that kind of roughly matches. And that's how you do it. Any other questions? OK. So, you know, about hopefully a little bit more than halfway through the talk, I'll say a little bit about image modeling, image-based modeling, and maybe touch briefly on photo tourism. And then we'll move to sort of the interesting open problems in reflection and transparency. So, you know, I've used the word image-based rendering a lot. You take images, you render new scenes. What is image-based modeling? Well, around the same time as people were doing image-based rendering in the mid-90s, computer vision people said, let's call this image-based modeling. Yes, question?
Could you define modeling and rendering?
Sure.
But must be sort of slightly different from each other, and what are they?
Mm-hmm. So modeling, I would say, in this context, I mean, modeling could mean something like taking clay and building a model, right? But in the context of computer vision and graphics, modeling is the process of going from images to a three-dimensional representation. And rendering is going from a three-dimensional representation plus maybe other information like lights to a finished picture. So that's rendering. Yeah.
Thank you.
Mm-hmm.
Unless it's image-based rendering.
Unless it's image-based rendering, in which case you start with images in and images out. Right, exactly. That's right. Good. So Pedro got the whole story there. So image-based modeling, I think it was the Debevec-Taylor-Malik paper that introduced this name. But basically, they built these really nice, simple block models of architecture on Berkeley campus, and then they created a movie where you could fly around sort of from live action around the synthetic model and back into live video. And it was an interactive system, so the user would say, put a block here, put a pyramid here. But it had a lot of very interesting components, this idea of using sort of parametrized three-dimensional models. So these days people might call this model-based vision, meaning that rather than not knowing anything about the scene, you assume there are planes in the scene, or there are cylinders, or something like that. And with this system, they were able to figure out where the cameras were. And another important idea they introduced was this idea of view-dependent textures. So if you're going to put color on the surface of a model, rather than just blending all the colors and getting a consensus, remember the original images. And when I'm trying to render a virtual viewpoint, like that red camera over there, I will sort of use the view 1 a little bit more than I will use view 2 because it's closer. And with that kind of thing, even if your model doesn't have very small indentations for windows, your eye believes they do because you're crossfading between images and you think you're seeing the relative motion, or if there's a little bit of shininess. So really, this idea of view-dependent texture mapping and what Chris Bueller did in unstructured lumigraphs is almost the same thing. But it's just a nice way to think about things. You know, texture maps are photographs you apply into the scene. The best photographs are the ones that are near your viewpoint. And the quality of sort of automated 3D reconstruction, image-based modeling, continues to evolve. So I'm going to show you something from 2009, which is an aerial flyover of a synthetic model generated from aerial photography. So in Graz, we have a team that builds the models for our aerial mapping, and they built this video. I think the video has just paused, so I'm going to let me restart this. Okay. Where are we here? I'm going to have to bring my mouse back. Sorry about that, but okay. So let me see. We were here. you guys can't really see what's going on because it's still showing that, but I think the PowerPoint is frozen. So what I might do, I'm going to try to decide whether to jump to all right. So I really apologize for this, but it does look like the computer, it just doesn't want to respond right now. So I may have to just reboot. Okay, finally. I got rid of the PowerPoint, so let's just restart here. Okay. Should be back in a minute. Okay. So let me just sort of jump to where I want it to be. Okay, so the next topic I was going to talk about was phototourism. Phototourism is the system we developed at the University of Washington, where rather than assuming you had a person take a collection of photographs in a very structured way, we would take photographs off the internet and then basically build an interactive experience. So I think you saw the video at the beginning. But basically from the photographs we can go to this point cloud model, which also tells us where the cameras were originally located. And then we can render a video like, let's see, is it going to play? Okay, so it doesn't want to play the video. Let's just skip over that. Okay, so the interesting thing about that phototourism was that it was sort of an early example of internet computer vision, where you go out to the internet and you collect photographs. And there's been a lot of interesting work since then in this area. So one of them was James's work here on scene completion, where basically if you want to fill in the hole, that white thing, you want to remove the building, you will go out to the internet and find similar images and then paste little bits of those images back into the original thing. So this was like one of the early interesting things where you take the sort of photographs from the internet and do something interesting. And since then, so what do you do with 1 million images? You have a database taken from the web. Since then, there have been a lot of other interesting pieces of work, like James and Noah had a course on this. James was talking about some of the ways of identifying locations by matching them against internet photos. And there have been a whole series of courses taught at various universities. So Lana Lezebnik had one. There was Tamara Berg. There was a workshop on the topic, recent workshop at ECCV. And James even has this course right now on data-driven vision and graphics. So internet computer vision is just one way of saying there are lots of images out there. The internet is a convenient source for it. But the abundance of data allows us to do things that we couldn't do before, right? And this is, the key to cracking the puzzle of how to do speech recognition has turned out to get more and more training data. And we're sort of hopeful that this will also allow us to do all kinds of breakthroughs in computer vision. So some of the recent research that we've and others have been working on are building better 3D models, like using piecewise planar models for architectural scenes, or for building interiors where everything is axis aligned, so that using little cuboidal models turns out to work well, or just pushing the boundaries of multi-view stereo. So on the left is sort of the sparse reconstruction you can get out of PMVS, which is Yasu Furukawa's thesis work. And on the right is what happens if you kind of work harder and try to get more and more dense 3D geometry, and then you can fly around in these things. So, sort of I want to ask here, sort of the final question is what's missing? And I would claim that things like reflection and gloss are missing from the examples that you saw before. That basically if we look in the window, you can see things through the window and you can see the reflection. And then the question would be, well, how do we deal with that? So what I'm going to do is just switch decks here. And we're going to look at, let me see here. Okay. Reflections. Okay. So this is the SIGGRAPH paper from last summer. And yes.
Before getting to that,
sure.
there are also problems associated with homogeneous patches and
that's right.
repeated patterns and
Yep.
all these other things.
Those are all issues, and they're not going away.
Okay.
So in some ways, you know, the laser scanners are one solution. And the good news is that what used to be called laser scanners now can be bought for, what's a Kinect sell for? $150, I think. So, you know, you can get low-cost laser scanners eventually that have a limited range of throw and so on. But yes, those problems are also going to be with us. And, you know, you can try to do things like, for example, have higher-level architectural models for flat surfaces and things like that. But so I think it's inaccurate to say that the big remaining problem is reflections and gloss. It's one of the open problems, and so we want to do some interesting investigations into this. So, you know, these are just examples of how these effects, you know, are everywhere. So even on something like a table, there can be quite a bit of gloss. You look outside in a car. And so if you take a traditional image-based rendering system and you do the usual thing of let's build a 3D model and then let's kind of use the model to morph between input views, you get a result that looks like this. What you're seeing is there's a certain amount of popping because what's going on is that even though the model has reconstructed the wall and the bottles correctly, the reflection is moving in a different way than the bottles are. And when you cross-dissolve between different images with the appropriate motion for the bottles, the reflections are jumping. So the approach we use is to basically separate the scene into 2 layers and then render for that, and then it looks a lot smoother. So basically, if we put them side by side, it looks something like this. On the right is the original image-based rendering the way I've explained it to you in this lecture. On the left is one which has 2 layers, and I'll shortly explain what it means to have 2 layers. So this is another example of standard image-based rendering. And then when we have with reflections, and so again, looking side by side. So what do I mean by having 2 layers in this context, right? I talked about the foreground layer for the dancers and the background layer for the wall. In this case, it means something else. It means that there are 2 layers that are being added together. So there is different geometry for what we call the front depth and the rear depth. When you see a painting with glass in it, and you move your head, you're going to see the painting move at the apparent depth of the painting. What you're going to see in the glass is a reflection of the scene. And if the reflector is flat, if it's a mirror, that reflection is a virtual image at the correct depth as if you were behind the thing. In other words, you could be looking at something that was, you know, a window into a faraway scene, right? And so that's why we call a front depth and a rear depth. It's sometimes hard to say which thing is the reflection and which thing is seen through. If you're standing very close to a window and you're looking through the window at a faraway scene, the reflection, which is you, is actually much closer than the buildings you're seeing through the window. But our system can just reason about near depths and far depths, and so we just call it the front and the rear depth. And then what we're going to do is basically take the image sequence and do the usual pipeline of trying to figure out where the cameras are. And after that, we're going to extract the depth. So we're going to do stereo matching in a way that it tries to get 2 sets of depths. So here in red are the pixels where it thinks there are 2 depths. And then once it has this kind of reconstruction of the scene with 1 or 2 depths, then it's going to take those depths and we simplify the scene in terms of little local piecewise planar things, and that's the reconstruction. And then in the last stage of our pipeline, we're going to actually pull apart the colors. So we're going to say which of the light came from the wall in the painting versus which of the light came from the reflection. And I'll show you a little bit more details about each of these pieces. So, yes?
Just out of curiosity, does that mean that you could also resynthesize a video where the glass wasn't there, for example, and there was no reflection? Is it a clean enough separation you can do that?
That's a great question. So the theory is if this did what we wanted to, if it really correctly separated the front light, the reflection from the thing, you could do that. And that could be very useful, like if you're just driving down a street and you want to see what's in the shop windows and all these reflections are distracting. So yes, that's the hope. In practice, the actual results have certain degeneracies. I'll talk about a little later because it's easier once you see what the degeneracy is. That in an earlier work we proved are sort of there and are very hard to discover. Basically, if the motion is mostly one-dimensional, any long elongated strip of highlight is very hard to pull because you don't see that where the values change. So you can write it down as a theorem that says that if there is no absolute black pixel in the scene, there's always some ambiguity about which color goes where. So if the darkest value in your scene is like a dark gray, it's quite possible that that dark gray is part of the base reflection or part of the base color. Yeah. So we start with a stereo algorithm which does usual sort of plane sweep thing, and then we get this kind of a cost volume. And here you can see this is the depth, for example, of the wall and the painting, and this is the depth of the reflection. So we basically figure out where we have two things, and that lets us basically, again, this shows where there are two different depths going on. And so what we do is we label the scene as to where we think it has one or two depths, and we call that the reflectivity. So the pink areas are the ones where we only think there's one depth that's not reflective. And then we extract the depth values in both layers. So this is sort of the input we need. This tells us how to line up the images, assuming the motion was due to the front depth or the back depth. And that lining is going to be important in order to pull the colors apart. So then what we do is we pull the colors apart, and the actual solution is a kind of a constrained least squares. And this is to address your question. These white stripes here are not actually part of the painting. They are the image of these white things here in the scene that were basically large extended areas of white. And because the camera only moved sideways, it couldn't tell what belonged to what. It gets a lot better if the camera moves like this, but that's not as common when you're driving along a street, something like that. Yep. Yep. So the final stage after we've done the decomposition is to have a rendering system. And the nice thing is you can put this all on a GPU and render this at interactive rates. And that's what gives us the final result. So I'll show you just one more example, and then I'll switch back to the other talk and wrap up. So again, one final example. There's what it looks like with a single layer. You'll notice that the lights are jumping. And then when we go to the two-layer thing, it looks a lot smoother, right? So that's basically the essence. And this is still an unsolved problem. You see certain visual artifacts in ringing, the ability to accurately estimate where the boundaries are of what's reflective and what isn't. Like you might notice sometimes the light drifts a little bit outside the frame of the picture. These are still all open problems. So, yes?
If you have a glass cube around an object that's not a plane,
that's right.
Does that cause problems?
So, I mean, the glass cube itself isn't a single plane, but each of the planar facets will introduce a different reflection, which would be a different additive thing. We only did this for a two-layer model. You can easily arrange multiple planes of glass, each of which is reflecting slightly differently, and then you need an n-layer model. So it affects it that way. The other sort of question you didn't ask is, what if the reflector isn't actually planar, right? Is a ball, right? So if the ball is shallow, like your shaving mirror, for those of us who still own shaving mirrors, right? You can get a stable virtual image that is just at the wrong depth, right? So slight curvatures don't matter locally. What matters a lot is undulation. So as soon as you have something that is a very wavy thing, your reflections will kind of start moving, and they might even move in a way where the epipolar geometry isn't correct. So with a planar reflector or a parabolic mirror, you will get a stable virtual image, which means when you move sideways, pixels only move sideways. With an undulating reflector, all bets are off. So that's one of the areas we'd like to explore in the future by basically going from stereo matching to general 2D flow, is to be able to say, oh, okay, things move like this, and now I use some kind of a two-dimensional warp field to account for what's happening to the reflection. Yeah. Okay, well, let me just wrap up so we have a little bit of time for questions. I think, let me see where we are in this talk. Okay, let's wrap up. So what I've talked about today are a range of various things in image-based rendering. At one end are the pure representations like a light field, which is just samples from four-dimensional ray space, no geometry. The Lumigraph actually has a crude 3D model, which in my mind makes it more powerful. On the left edge would be classic texture map models. You build a 3D talking head, you paint color on the skin, it looks okay, but You know, it doesn't have any real gloss. And then in between are all these various hybrid techniques. You know, we talked about some of them, like sprites with depth and view-dependent texture and things like that. So, you know, what works, what doesn't? As it turns out, you know, from the work we did for phototourism and other subsequent work, in general, for a textured scene, you can usually figure out where the cameras were. We don't need some special IMU system or whatever. You can tell where the cameras are. You can do fairly well for textured scenes like aerial modeling. Again, you know, I work with the people at Microsoft who build the aerial maps. And for some complicated buildings or a structure like the Space Needle, that's this big dish on top of a pole, you know, the height field models don't work. But generally speaking, textured modeling or even modeling from ground level, meaning, you know, van pictures works pretty well. But it's really hard to always get accurate boundaries in matting. As Ben mentioned, textureless regions, repeated textures are an issue. Reflections and transparency, I would claim, are an interesting open problem. And you know, user-generated content is really where, personally, I'm very excited. So there are commercially acquired content where it's very structured. You more or less know where the vehicle or the airplane was. And then there's user-generated content, which could be photos from the web taken different times of day or different seasons. So that makes it a lot more interesting to match these kinds of things. And of course, we have new sensors coming down the line. There is active sensors that project structured light into the scene to make the stereo matching easier. And there are planoptic cameras like the Lytro. How many people have heard of the Lytro camera? About a half. How many people have seen one? Few. Okay, right. But they're basically cameras which, after taking the picture, because they have a whole lens array, will let you refocus the image and change the viewpoint a little bit and things like that. So these are all interesting new things in this area. And the final thing I think that is really a great open problem is integration with recognition, because all of these things will get a lot better if we can recognize what's in the scene, we can build better models. Now there is one very closely related field to this, which sometimes overlaps so much it's hard to tell them apart, but that's computational photography. So computational photography, you know, I talked about image-based rendering as images in and some sort of interactive experience out. Computational photography is very similar to this. It's taking images in and creating a more beautiful image. And some of the things like panoramic image stitching are claimed by both fields. You know, they're basically perfect examples of each one. And frankly, most of the researchers span these two fields anyway. But this is a very interesting area. For those of you who are interested, there's a conference starting tomorrow at Harvard over the weekend. So it's a good place to go and catch up on this. So I think with that, I'll stop with this slide and take any questions you might have. Yes, Spike.
So when I make this picture, I put a third point. That line becomes a triangle.
Mm-hmm.
Down the bottom are drawings.
Oh, yes.
So
okay.
Drawings have the property that you can extract them from images or from geometry, or
right.
There's a whole bunch of possibilities in there.
Sure.
And one thing about drawings is, what are the features we tend to put in drawings? Mm-hmm. Well, boundaries.
That's right.
And highlights that arise from specularities.
Yep.
And stuff like those are sort of the first couple of things you want to put in there.
That's right. Yeah.
Which are exactly the two things you said you couldn't handle.
Right.
So what I'm wondering about is there some reason for that? Is there a reason that the things we're sensitive to,
right,
the things that we tend to be sensitive to and therefore want to include in a drawing,
right,
are the ones that are hard to deal with?
No, it's a great question. I don't know if I can come up with a philosophical enough response to do justice to your question. But the reason I say boundaries are hard is actually boundaries are very often the one reliable shape cue that we can use. And in stereo matching, if you have a textureless frontal object against a textureless background, the boundary is what you're matching on. But that also creates a problem because since it's the only cue to actual depth, it's very easy to push that depth into the background and get confused about what the background is, right? So I don't know, obviously good artists try to depict three-dimensional shape as well as information about identity and structure, right? And they use various cues. They will use perspective in backgrounds. They will use cast shadows. They will use hatching on the front to sort of indicate, foreshortening in texture and things like that. So there's a lot of cues, right? The highlight is an interesting one because the presence of a highlight tells you something about the surface normal and the lighting direction and the amount of gloss, right? But it confounds all of those. From a single image, it's hard to pull them apart, right? So from an artist's point of view, it definitely lets you tell whether the apple is dusty or freshly washed, right? From a computer vision point of view, if we're trying to get accurate 3D shape, it's sometimes hard from a single image, right? And when you have multiple images, you just have to be careful so that the highlight motion doesn't get confused with the texture motion. So I gave kind of an engineer's answer to what was a very artistic question. Anyone else? Yes?
What about shadows?
What about shadows?
Yeah.
So shadows are very interesting. They definitely, you know, they're extremely important in rendering. For example, if you render a computer graphics character and you forget to put the shadow of where the character is walking on the ground, you totally lose the illusion. I mean, they're wonderful optical illusions, right, based around the lack of shadows. For whatever reason, there aren't that many publications. I mean, you know, I saw nice work today on just extracting intrinsic images where the shadows are important factors. In three-dimensional computer vision, they tend not to be used that much. Now, if you're looking at one particular scene with a rapidly moving camera where the sun isn't moving, the shadow almost becomes just a part of texture. In other words, you can capture as part of the texture, right? If you're talking about other things like a collection of photographs taken of Notre Dame at different times of day, then the actual cast shadow can start to give you cues. You know, especially if you know the latitude and you know the trajectory of the sun. So there have been a few point publications in computer vision about using shadows to infer shape. Nice work from the Mitsubishi lab on looking at time-lapse photographs and trying to pull apart what the cast shadows are from other kinds of illumination. So there's definitely work in there, but I have not seen widely used commercial systems like the ones we use for example, aerial mapping that use the shadow information. You know, for one thing, when you fly an airplane in a grid, by the time you come back, the shadows have moved. For another, it seems to be less immediate than the kind of triangulation you get from just looking at a scene from two different points of view. But it's important, and you know, certainly if we want to take scenes and manipulate them and place objects in different areas or change the lighting or something like that, being able to tell where the shadows are is very important.
Okay, let's thank Rick again. So reception outside, we'll be able to ask more questions.
Okay. Thank you.
When I was asking the question about how